Everyone, my name is Jimmy Yang. Today I will introduce to you the concept of column ideal. I use the paper of Pete Clark to read the concept here. It is a paper about the CM elliptic curves over real number field. Let R be a domain with frictional field K. For frictional R ideals I and J, we define the column ideal J column I is equal to a set such that S belongs to K such that X times I is belong to J. It is also a frictional R ideal. The column ideal is a frictional R ideal, and if I is invertible, then J column I, which is a frictional R ideal, is equal to I inverse J. J column I is equal to I inverse J. Let E defined over F is an OCM elliptic curve defined over a number field F. Let I be a non-zero ideal of O. We have an I-torsion kernel. I-torsion kernel means a cyclic subgroup of N-torsion group of E, elliptic curve E. And E bracket I means E bracket I bracket means a set such that S belongs to E, such that for every alpha belongs to I, alpha times X is equal to 0. So I is the kernel here. E bracket I means the kernel of I. If I is contained in J, then E bracket J bracket is contained in E bracket I bracket. Since I contains the positive integer, of the index of I inside O, so E bracket I bracket is inside E bracket index of I bracket. Thus, E bracket I bracket is a finite O module. E bracket I bracket is a finite O submodule of E. Evidently, E bracket I bracket is stabilized by the action of G of K. So it corresponds to a finite tail Fk subgroup scheme of E. If Fk does not contain F, if Fk is strictly bigger than F and contain F, but not equal to F, then the non-trivial element of C of Fk over F acts as a complex conjugation on endomorphism algebra of E, and thus the E bracket I, the conjugate of E bracket I, is equal to E I bracket. Thus, the conjugate of E bracket I is equal to E bracket conjugate of I. If Fk is bigger than F, but Fk contains F but not equal to F, then there is a non-trivial element of the automorphism of Fk over F, which acts as a complex conjugation on the endomorphism algebra of E, and thus the complex conjugation of E bracket I bracket is equal to E bracket conjugate of I bracket. It follows that E bracket I bracket is defined over F if only if I is real. If only if I is real. For any non-zero ideal I of O, we have an isogeny from E to E quotient by E bracket I bracket defined over Fk in general and over F if I is real. Let iota is a map from F to C be a field embedding, thus E is isomorphic to E lambda for some proper O ideal lambda. Observe that the kernel of the natural map from E lambda to E lambda column I. Observe the kernel of the natural map from E lambda to E lambda column I is the kernel is lambda column I quotient by lambda is equal to C quotient by lambda bracket I bracket. So E quotient by E bracket I bracket is isomorphic to E lambda column I. E quotient by E bracket I bracket is isomorphic to E lambda column I. Okay. Furthermore, if I is invertible, then E lambda column I is equal to E I inverse lambda. Thus, we get an explicit description of I-torsion kernel and the associated isogeny in terms of uniformizing lattice. So, we understand it now that E quotient by E bracket I bracket is equal to E lambda column I is equal to E I inverse lambda. So we get an explicit description of I-torsion kernel and the associated isogeny in terms of uniformizing lattice. Let iota is a F to R field embedding. By lemma 3.2, we may choose lambda to be real lattice. Suppose that I is moreover real, then lambda column I and thus so lambda column I is also real, and thus E lambda, thus the map from E lambda to E lambda column I is an explicit description of I-torsion kernel and the associated isogeny in terms of uniformizing real lattice. Okay, theorem 3.9, let delta be an imaginary quadratic discriminant. Let F is inside R. F is contained inside R. Let E over F be an OCM elliptic curve. Then there is an OCM elliptic curve E prime such that E prime is isomorphic to EO. And an F rational isogeny phi. F rational isogeny phi from E to E prime. Let n be a positive integer which is prime to delta. Then the isogeny of phi of part A induce a GF module isomorphism from E bracket n bracket to E prime bracket n bracket. Proof: there is a primitive proper real or ideal lambda such that E is isomorphic to E lambda. Let I be any proper real or ideal. As above, there is an F rational isogeny phi I from E to E quotient by E bracket I bracket, which over R is given as E lambda from the map from E lambda to E lambda column I, which is equal to E I inverse lambda. Taking phi is equal to phi lambda established part A, the degree of phi lambda is equal to the index of lambda inside O, which is by corollary 3.8 divided the discriminant. It follows that the degree of phi lambda is prime to n. Thus, phi lambda is a map from E bracket n bracket to E prime bracket n bracket, because degree of phi lambda is prime to n. That is the setting here. That in the theorem here, let delta be an imaginary quadratic discriminant, and let n be a positive integer, which is prime to discriminant. Then phi lambda is the degree of phi lambda is prime to n. Thus, phi lambda is a map from E bracket n bracket to E prime bracket n bracket, and which is a kind of isomorphism. Because degree of lambda is prime to n, which is required in the theorem here. That in the theorem here, n is a positive integer which is prime to discriminant delta. Remark. Okay, that is basically what's happened here. We understand that the quotient map is isomorphic to isogeny, and the map from E lambda to E lambda column I is an explicit description of I-torsion kernel and the associated isogeny. Okay, and we can see it now that the isogeny, there is an F isogeny, F rational isogeny, phi I from E to E quotient by E bracket I bracket over R, and is given by E lambda to, is given as a map from E lambda to E lambda column I, and it can be viewed as a map from E lambda to the E I inverse lambda map. And taking phi is equal to phi lambda, establish the part A, and the degree of phi lambda is the index of lambda inside O, which divides discriminant delta. It follows that the phi lambda is prime to n, and thus the phi lambda is a map from E bracket n to E prime bracket n, which is also isomorphic. Okay, bye bye.